Hello, I'm Daniel from the University of Wisconsin-Madison, and this is VRSight, an AI-driven virtual reality scene description system for blind and low vision people. My collaborators include Justin Feng, ZX Ching, Daniel Wang, Rithvik Dyava, Yapeng Tian of UT Dallas, and my advisor, Yuhang Zhao. Virtual reality is transforming fields like socializing, education, and healthcare, but VR remains inaccessible to millions of people who are blind or have low vision. Current VR devices like the Meta Quest rely almost exclusively on visual cues like on-screen text and outlines around interactive objects. But these immersive interactions like pointing and hand tracking are completely inaccessible to blind and low vision users. Furthermore, current techniques rely on XR developers to implement accessibility features. Our prior work, XR for All, interviewed 20 industry developers and revealed why they deprioritize accessibility. For example, rapid development cycles, lack of formal XR training, and that developers systematically overestimate accessibility implementation costs, viewing people with disabilities as edge cases rather than a substantial market. This problem creates a vicious cycle. Developers perceive that most people with visual impairments don't use VR, reducing motivation to implement accessibility features, so most mainstream VR applications remain completely inaccessible. To challenge this perception, we need post hoc solutions that overlay accessibility features on existing applications without developer intervention or access to underlying code. While post hoc systems exist for 2D web accessibility, VR lacks comprehensive solutions. The only similar VR tool is Yuhang Zhao's Seeing VR, providing overlays for low vision users with 9 post hoc tools, but it requires developer integration for 5 additional features. No post hoc system exists for blind VR users until now. We present VRSight, an AI-driven system that makes VR accessible without requiring developers to rebuild their applications. VRSight is a post-hoc 3D screen reader that works with existing VR applications using off-the-shelf hardware. Unlike traditional 2D screen readers that provide linear descriptions, VRSight conveys environments where objects are scattered throughout 3D space, telling users not just what objects exist, but where they are. At its core, a screen reading system needs to be able to identify the objects in a virtual scene. However, state-of-the-art object detection models trained on real-world images completely fail to classify virtual objects. Like this YOLO V8X model trained on the popular COCO dataset, identifying 0 objects correctly. And the one object it does find labels a game cartridge as a cell phone with only 25% confidence. To address this additional gap, we created DISCOVR, a dataset of 17,691 labeled images from 17 popular social VR apps, covering 30 categories of virtual objects like avatars, interactive elements, signs, and safety boundaries. To collect DISCOVR, 6 researchers recorded at least 20 minutes of VR gameplay across all apps, ensuring to visit at least 3 different environments per social VR app. We extracted 1 frame per second from recordings and randomized upload order to minimize similar frames. Researchers manually annotated using open coding, starting with 300 images each, then met to agree on a master list of object classes. From there, we annotated about 2,000 images each, split images into a standard train val test split, and generated 3 augmentations on the train split to come up with our final image total. Compared to the COCO YOLO V8X model, which couldn't detect any objects, our fine-tuned YOLO V8 model on DISCOVR can support classes including the user's hands, signs, buttons, and other interactive objects on the table, achieving 67.3% mean average precision to outperform the base model. Now that we have an object detection model, VRSight integrates 5 AI components working in real time. Fine-tune object detection, depth estimation for spatial positioning, laser detection for VR pointers, and language models for scene analysis and speech generation. To accurately place our audio descriptions, we can take the 2D components from our object detection model, but we also need a depth estimation model to understand relative distance in 3D space. Spatializing audio descriptions is important to help users self-locate in VR and for immersively blending our audio descriptions into existing audio in the scene. Now, one of the most common VR interaction techniques besides grabbing, is pointing at objects and menus. While we can detect hand positions using object detection, we need to identify the virtual laser with another method. So we use traditional computer vision edge detection approaches to judge where you're pointing and read objects at the end of the virtual pointer. After querying for descriptions, we use optical character recognition to read embedded text, and since immersion is a key tenet of VR, we also match the tone of our audio descriptions to the scene's atmosphere. Here, we have Oculus' first steps, described as cheerful.
Two hands are reaching toward various interactive elements on a surface with a sign displayed in the background.
Compared to this spooky Halloween scene identified as fearful.
A pink ghost is floating near a brightly lit mansion at night.
We spatialize audio descriptions using stereo panning for direction and volume scaling for distance, delivered through a web VR utility for real-time feedback. To demonstrate VRSight's effectiveness, we designed 4 interaction methods following a general to specific approach from broad orientation to targeted exploration. For time, I'll demonstrate 2 key interactions. Scene sweep, which scans left to right, playing spatial audio for each object.
Reading all objects. You are currently muted. Menu, black background, white text, pink lines, circular notes.
And second, Safeguard automatically warns users approaching VR boundaries, a novel safety feature since current boundary systems are visual only. We conducted a user study with 9 participants who are blind or have low vision. Most had little to no VR experience, and those who did cited inaccessibility of the platform. Instead of a researcher-oriented demo scene, we demonstrated the efficacy of our post hoc system by evaluating in Rec Room, one of the most popular social VR applications. All tasks were common interactions in social VR gameplay. For example, we asked blind participants in our local area about some difficulties they've encountered in real or virtual social environments, and one frequent challenge they cited was finding an open seat. For this seat finding task, we positioned participants at a conference table where one seat was occupied and one remained open. VRSight notices when avatars are near seats and marks them as occupied, separating likely occupied versus available seats. Results were encouraging. 56% of participants successfully located and sat in available chairs. 67% correctly accounted avatars in dynamic social environments, and participants identified 4 to 12 objects in room exploration. Users adapted interaction strategies based on a task complexity. We consider VRSight a real-time system as our end-to-end latency was measured as low as 2 milliseconds running on standard gaming hardware. Finally, while VRSight aimed to improve accessibility of current VR interaction techniques, gestures like pointing are not intuitive or tiring for users. So we invite you all to help us improve upon interactions with VRSight. And to help you do so, we've open sourced the system, Discover dataset, and our trained model weights to github.com/MadisonAbilityLab/VRSight. VRSight demonstrates that post-hoc AI solutions can make existing VR applications accessible without developer intervention. By combining object detection, depth estimation, and contextual audio generation, we've created a functional 3D screen reading system that works across multiple VR platforms for both virtual and mixed reality applications. We hope that by open sourcing the work, we can increase user adoption of VR and future research in innovative interaction methods. We believe VRSight bridges a large gap between advancing VR technology and users' accessibility needs, proving that emerging technologies can be inclusive by design rather than exclusive by oversight. Please see our paper for more details, and if you have any questions, please let me know in the comments. Thank you.